We've been talking a lot about exponents. In this video, we're going to take it a little deeper and talk about rational exponents. But first, let's talk about this word rational. In math, we label different types of numbers. So one category of numbers that most people know about are whole numbers. We also have integers. Rational numbers is another type of number, and so that's how we're using that word here. And then there's also irrational numbers. So a rational number is any number that can be expressed as a fraction. So for example, 1/2 is a rational number because clearly it can be expressed as a fraction. But 2 is also a rational number because we can always write it as 2/1. You could have negative fractions, such as -3/5. Even 0 is a rational number because we could always think of it as 0/1. Decimals, such as 1.5, would be a rational number because it can be expressed as 3/2. So now you might be thinking, well, what's not a rational number? Well, those would fall in the category of irrational numbers, and examples of those include pi, which we usually approximate as 3.14, but it is a decimal that goes on forever and never repeats. And so unlike the 1.5 decimal that we can convert to a fraction, when a decimal never terminates, we cannot get that to be a fraction. Another irrational number that we've seen lately would be the square root of 2. We leave it as the square root of 2 because if we convert it to a decimal, it's a decimal that goes on forever. In other words, it's an irrational number. So that gives you an idea of what's rational and irrational as far as numbers are concerned. So what we're going to be working with in this video are rational exponents, or another way to think about that is fractional exponents, or exponents that are fractions. In other words, we're going to be looking at things like x to the 1/2 power. Now, in order to show you what's going on with these, I'm going to first remind you of some different things we've talked about so far to kind of warm our thinking up so we can understand what's going on with these rational exponents or fractional exponents. So first, recall that the square root of 9 equals 3. In other words, what I want to emphasize here is that when we square root, we undo the squaring of the number. Or you could think of that as a square root unsquares. We could talk similarly with the cube root. So if we had the cube root of 27, we've seen that that equals 3. And the reason why is because a cube root uncubes, and so on. A fourth root unfourths, etc. Alright, so I just wanted to remind you of that idea of radicals undoing exponents. And now what I want you to do with your thinking is set that idea on the back burner, and I want to remind you of another idea we've talked about recently. And that's what happens when we take a power to a higher power. And what we've seen happen there is this one that I've written down here is saying that's a squared to the third. So we're taking a squared times itself 3 times. But the simplification of what's happening with that when we simplify it is that we end up multiplying the exponents. And that's going to give us a to the 2 times 3. Now, I know that equals a to the 6th, but I really want to hone in on the fact that we are multiplying exponents if we apply the pattern of what's happening when we take a squared times itself 3 times. What we're doing is multiplying the exponents, or compounding the exponents by a factor of 3. Alright, so now we've recalled that radicals undo exponents, and then if you have a power to a higher power, you're going to end up multiplying those powers. Now there's one more thing that I need to review with you before I'm ready to put all these details together. In particular, I would like us to look at fraction multiplication, and this is just a review of what that looks like. So let's say, for example, we have 2/3 times 4/5. When we multiply fractions, what we do is multiply the top numbers, the numerators, together, and we multiply the bottom numbers, or the denominators, together. In this case, that equals 8/15, but I'm really just wanting to remind you of how you multiply fractions, which is to multiply across the top and separately to multiply across the bottom. You can then reduce, or you can reduce before you multiply, but just trying to bring back the memory of learning fraction multiplication. So we've reviewed three things here. First of all, that a square root unsquares, a cube root uncubes, etc. Next, we looked at, to simplify a power to a higher power, we multiply the powers. And then last, we briefly looked at fraction multiplication. So now let's start dumping all these ideas in the same pot to see what's going on here. Consider a squared to the 1/2. Now, this is a power to a higher power. The way we would simplify this is to multiply the powers. So we get a to the 2 times 1/2. Well, 2 halves is going to be 1, so this gives us a to the first, or just a. Alright, let's look at another one. Let's say we have a to the third, and we raise that to the 1/3 power. We're going to multiply those exponents, and when we actually do that multiplication, we're taking 3 times 1/3. Well, 3/3 is 1 whole, so we get a to the first, which just equals a. Now what I want to do is run these ideas alongside what we've seen happen with radicals. In particular, consider the square root of a squared. Well, we know if our index is a 2 and our inside power is a 2, they cancel each other out. So this is just simplify to an a. So when we take a squared to the 1/2 power, we got an a, and when we take the square root of a squared, we got an a. It seems like they're doing the same thing with the numbers. Similarly, if we were to have the cube root of a to the third, then that index and that exponent will cancel each other out, giving us just an a. So in this case, when we cube rooted a number, it behaved in the same way as when we raised it to the 3rd power. And that's because of how the multiplication of fractions work. So we got an a and we got an a. Hopefully you can imagine if we extend this property to other powers, it'd work the same way, because when we're multiplying this power to a higher power, the fraction and the non-fraction exponent are canceling each other out because they essentially are inverses or reciprocals of each other. So this isn't just a random pattern that's happening, and it's not a coincidence. This is because they are operating in the same fashion. And so this gives us a property in math. B to the fraction 1 over n is the same thing as the nth root of b. Now sometimes when it's all the letters, that bothers students a little bit, but that's just the very formal way of saying something like b to the 1/2 is the same thing as the square root of b. And remember, that gives us an index of 2, and so that matches our n here. That's the denominator with the fraction. And don't lose yourself on the abstraction. That's exactly what we were seeing up here in this first illustration, just written as an algebraic property. If I were to take this second part and write it out in the same way, what I would be saying is that b to the 1/3 is the exact same thing as the cube root of b. So basically, when you have these fractional exponents or these rational exponents, their denominator corresponds to the index of a radical. Their denominator corresponds to the index of a radical that's doing the exact same math operation. So this is just an example where we see that notation in math, as long as we obey the rules of the operator, there's actually two different ways to denote the exact same operation taking place. Let's do an example to see what this would look like in a problem. Alright, example 1, our directions are to evaluate, and we have a 25 to the 1/2 power. So what we've seen is that this corresponds to the square root of 25, which we've already looked at and know that that's 5. And that's all it is just recognizing that these fractional exponents correspond to radicals of some sort. So let's say we have 16 to the 1/4 power. So for me, the easiest way to process this is to recognize it as a 4th root of 16. Now, if it were a square root of 16, it would be a 4, but I've been tricked by that before, so I remember that the 4th root of 16 is 2. If you need to work through the process on that to convince yourself, you're welcome to do so. But that's the idea. Just take the fractional exponent, relate it to the radical that it corresponds to, and then evaluate that radical. Now what we need to do is look at a slightly more complex case that happens when dealing with these fractional exponents. To see that, consider x squared to the 1/3 power. Now, if I'm just thinking in terms of fractions and I want to simplify this, what I do is I multiply my exponents. So I take 2 times 1/3, and then here, if you need to, it's important to remember that my 2 is considered over 1 in fraction land. And so then when I multiply those, sorry, this should be a 3. There we go. When I multiply 2 times 1/3, what I get is 2/3. So in this case, it didn't simplify any because the numbers don't interact in a way where anything cancels out. Now, if I take a different root on this problem, and I just consider the fact that this 1/3, what we've seen with this 1/3 is that it actually corresponds to a cube root. So if I just go straight to applying that instead of multiplying exponents, what I would get is the cube root of x squared. So what I'm trying to illustrate with this is the connection between these two expressions. When we have a fractional exponent that doesn't have a 1 for the numerator, what that works out being is it stays an exponent when it converts to a radical. The denominator still translates into the index, but the numerator stays an exponent inside when it's converted to a radical. So if I wrote out the property for that, it would look like this. X to the m over n corresponds to the nth root of x to the m. We could also write that with the exponent on the outside, so that we have x to the m over n corresponds to the nth root of x to the m outside the radical. And the reason why we can do that is if you come back here to this x, if I had a similar example of x to the 1/3 and then squared it, my multiplication would still give me the same result because order with multiplication doesn't matter. So I'm still going to get x to the 2/3. So it really doesn't matter if I consider the radical and then put the exponent outside or put the exponent inside. Now let's look at this property where we have both an index and an exponent needing to be translated. Let's look at an example that deals with this for us. Let's say we have 25 to the 3/2. Now if I convert this to a radical, the index is telling me it's going to be a square root. I'm going to write that in red because we don't normally write it, but I want you to be able to see the number. So it's going to be the square root of 25, and I'm going to put the third power outside the radical. Okay? And so, again, to highlight where the numbers came from and went to, my denominator became my index, and my numerator became a power, or state of power, I guess. Now when I simplify this, I know the square root of 25 is 5, and I'm still cubing it, and so then 5 to the third is 125. Now that process kind of highlights why I wanted to put the exponent on the outside of the radical, because if I had put it on the inside of the radical, I would have the square root of 25 to the third. Now I'm going to need to take 25 to the third before I square root, which would still get us the same result, but when you're doing this by hand, it's in general easier in math if you can make things smaller before you make them bigger. I kind of think through the same strategy when I'm multiplying and dividing, because remember, we can do those in any order. They're on the same level of the hierarchy, and so it's easier if we divide first and then multiply. Here it's easier if we take the square root first and then apply the exponent. For b, let's look at 27 to the 2/3. So this would give me the cube root of 27 squared. So my denominator becomes my index and my numerator becomes my exponent. Now the cube root of 27 is 3. I'm still squaring that, and 3 squared is 9. And that takes care of that. Some students get worried about remembering which one goes where, and I would just encourage you to think about what's happening, to remember this based on what's happening. When we have a fraction, the fraction bar means division. So basically what's meant when we say the fraction bar means division is the bottom number is what we're dividing by. The top number is what we're multiplying by. In a radical, the index is telling us what we're going to repeatedly divide by, and the power is telling us what we're going to repeatedly multiply by. In other words, the denominator makes things smaller, the index makes things smaller. The numerator makes things bigger, and exponent makes things bigger. So don't just try to memorize without any understanding of which number goes where, but if you think through what's happening with a fraction and what's happening with an index and an exponent, there's a logical reason why we're putting the numbers where we are putting the numbers. That'll help your brain hang on to it, and you win a debate with yourself on a test if you understand the whys behind it. We're going to do one more example here where we're going to evaluate a function. And this is kind of throwing several things that we've learned together into one problem. So here we're going to have f of x equals 3 times 4 to the x. So first we're going to find f of 1/2. That just means we're going to plug in our function. Where we see the x, we'll plug in a 1/2. And after that, we're following the order of operations. The order of operations says to do the exponent first, and I'm going to do that by first converting it to a radical. So that's going to give us 3 times the square root of 4. Then the square root of 4 is 2, so we have 3 times 2, which equals 6. Alright, now let's look at one that's slightly more complicated. We're going to do f of -3/2. So we're going to plug the -3/2 into our exponent. Now this is more complicated because we have a negative exponent and it's a fractional exponent. Well, negative exponents told us that that's really division. So this is going to become 3 divided by 4 to the 3/2. So I moved the negative exponent to the denominator and made it positive. And now I'll convert it to a radical. So that's going to be the square root of 4 to the 3rd. So make sure you're processing how all of that conversion happened. Once you get it converted, the math's not too bad. That's 3 over 2 to the 3rd, which equals 3 over 8. So if you need to back it up and kind of go through that whole process again to make sure you're tracking, I encourage you to do so, because that's putting together several concepts that we've learned over the past couple weeks into one problem. But that's the idea with fractional exponents. Go ahead and give some problems a try to see how it works out for you.